We're going to cover content in Chapter 3, Section 4. We're going to be looking at zeros of polynomials. We've seen this before. We've done some previous work with finding zeros of polynomials. As a reminder, that's where we let y, or f of x, be equal to 0. And then we either did factoring or quadratic formula. We solve for zeros a variety of ways. So we're going to be looking at zeros of polynomials, and we're going to bring in a different element of finding zeros of polynomials. As a reminder too, zeros could mean solutions or roots or even x-intercepts. So zeros of polynomials where y equals 0, also called solutions, roots, or x-intercepts. All right, we have the rational zero theorem. This is a tool that we can use to find all possible rational zeros of a polynomial function. Well, as a reminder, what is a rational number? So I'm going to take us way back to probably one of the first things we studied in this course. Let's talk about reminding ourselves and recalling that previous knowledge of what is a rational number. This is the college algebra review topics. And down here in question 4, we saw that the set of numbers in the form a over b, where a and b are integers and b does not equal 0, that's called the set of rational numbers. So, and we had some examples. So we had an integer on top and an integer on the bottom. We have an integer on top and an integer on the bottom, etc. Even the number 4 can be thought of as a rational number because I could make 4 a fraction over 1, where both 4 and 1 are integers. -6 is also a rational number because we can again make that -6, which is an integer, over 1, where 1 is also an integer. All right, and it's probably good to kind of look at an irrational number too. An irrational number is a number that doesn't terminate nor does it repeat. So we might see something like square roots of numbers. Now, notice that negative is not underneath the radical with the 7. It's not part of the radicand, so this is not an imaginary number. So these are all irrational numbers. Right here, pi never repeats nor ends. Square root of 3 might end on the calculator, but that's just because the calculator only has so many slots to put numbers. All right, and then as a reminder, rational and irrational make up the set of real numbers. So every real number is either rational or irrational. So rational are the nicer looking ones, and irrational, maybe not so nice looking. All right, so let's go back to our lesson. Okay, we're finding zeros, and the rational zero theorem is a tool or a method that we can use to try and find possible rational zeros of a polynomial function. So if a polynomial function does have any rational nice zeros, then it would come from a list that we're going to generate. So here's our little formula or guideline right here. Any possible rational zeros would come from a list that we generate, and the list that we generate comes from factors of the constant term, and I think I'm going to put absolute value right here around constant term, divided by the factors of the leading coefficient, and I'm going to put an absolute value here. So I'm going to define P to be the factors of the absolute value of the constant term, and I'll define the letter Q to be the factors of the leading coefficient. Using the formula P divided by Q, we can create a list of all possible rational zeros of a polynomial function. If we have no other information, we begin our search for zeros by testing these possible zeros, these numbers in this list. And we test possible zeros by dividing synthetically. We've done synthetic division to see if we arrive at a remainder of 0. All right, it'll come all together for us. Let's first practice generating the P over Q list. All right, let's use the rational zero theorem, which tells us let's list all the possible rational zeros of the given function 1, 2, and 3. Example 1's already been completed for us, so let's see if we can kind of see what's going on here to help us answer question 2 and 3. So in problem number 1, we have a cubic polynomial. The lead term is x cubed. So f of x equals x cubed plus 2x squared minus 5x minus 6. First thing I would suggest is above your constant term, I would put a p. And above your leading coefficient, the lead coefficient, which is found in the leading term, it's the number in front of that term, that is going to be called Q. So we've got P and Q, kind of backwards, I guess. All right, and I want to look at the factors of the absolute value of my constant term. So my constant term is -6, but for what we're doing, all we have to consider is just factors of 6. So P is defined to be factors of 6. Q is defined to be the factors of the absolute value of the number that's in front here, which is 1. Okay, and so then we find the factors of 6 and the factors of 1. So I'm going to come over here. If I'm looking for factors of 6, I know that I have the sets of 1, 6 and 2, 3. And so I think about putting these factors in order, 1, 2, 3, 6, which is what's done here, 1, 2, 3, 6. But also notice that not only do we have the positive factors, but we also want to include the negative factors. So that's why we put plus minus. Just because I could divide -1 into 6 and get a remainder of 0. I can divide -2 into 6 and get a remainder of 0. So it's both the positive and the negative. And if you're looking to save some pencil lead, you can actually write that set of factors, positive, negative, in this format, where you put plus minus in front of the set of factors of 6. So again, P will be the list of factors for the absolute value of the constant term. Q will be a list of factors of the leading coefficient. Factors of 1, the only numbers that go into 1 would be 1 and -1. All right, so we've generated a P list and a Q list, but the formula says we have to consider creating P over Q. So notice that right here in the numerator, P, we have all the factors of 6, and in the denominator, we have all the factors of Q. All right, this is equivalent to taking one at a time. I would kind of, just for right now, ignore the plus minus, and I would think about taking 1 and dividing it by 1. That results in 1. Then I would move on to the next number in the numerator, the next factor of 6 in the numerator. 2 divided by 1 is 2. So ones aren't necessary. The ones in the denominator aren't necessary. 3 over 1 is just 3, and 6 over 1 is just 6. And again, they condensed right here all those factors. So notice that we have 1, 2, 3, 4, double that for the negatives, 8 factors that we need to, or excuse me, 8 numbers in my list of P over Q, that if any of these numbers right here, or excuse me, if the function itself has a 0 that's rational, it would have to come from this list right here. All right, let's just practice generating P over Q lists for these first 3 examples, and then we'll put it together with other information that we've learned to complete the objective of finding zeros of polynomials. All right, let's create a P over Q list. So use the rational zero theorem to list all possible rational zeros of the given function. So this is P, and this is Q. So P, factors of 16. I'm just going to look at the absolute value. I know the constant is -16, but I'm just going to look at the absolute value. Well, for factors of 16, you can come over here if you need to. That would be 1 and 16, 2 and 8, and then 4 and 4. So trying to generate a list and then putting them all in order, I'm going to use the shortened version right here. So plus minus 1, 2, 4, 8, and 16. Don't have to write down the repeated factors. All right, Q. That would be the factors of 2. All right, well, the factors of 2 are just 1 and 2, so positive, negative, 1 and 2. Okay, notice how in example 2 now we have 2 different factors when you ignore the plus minus of Q. Up here we just had positive, -1. Now we have positive, -1 and positive, -2. So that's going to make us have a little more work. So P over Q. So the whole list for P over the whole list for Q. All right, so now what we do is that I'm going to take every number in the numerator, and I'm going to first divide it by 1. So every number divided by 1 in the numerator would just result in that number that's in the numerator. So plus minus, and I'll put parentheses here, I'm going to get 1 over 1, which is 1, 2 over 1, 2, 4 over 1 is 4, and 8 over 1 and 16 over 1. Now I'm not done. Now I have to go back because I have multiple factors of q. Now I've got to go back and take all the p's again, and now this time, instead of putting them over 1, put them over 2. So 1 over 2 is just a half. Yes, this is out of order, and that's fine. Then I'm going to take 2, the next number in the numerator, and put it over 2, but 2 over 2 is 1, and I already have 1 in my list. Now move on to the 4 in the numerator, putting it over 2. Well, 4 divided by 2 is 2. I've already got that in my list. 8 divided by 2 is 4. That's already contained here. And 16 over 2 is 8, and that's already here. So it looks like I've created a list of possible rational zeros for this function. All right, for the third example, this is P and this is Q. So factors of 3. Well, the only factors of 3 are 1 and 3. So plus minus 1, 3. Q is factors of 4. Oh, I should have put a 3 here. Factors of 4 are 1, 2, and 4. Okay, now let's keep going. We've just generated factors of P and Q, but we've got to create a P divided by Q list. So put P on top and Q on the bottom. Okay, so now again, we have to take all P's and divide it by 1, then take all the P values and divide it by 2, and then take each of the P values, excuse me, and divide by 4. So I'll start with putting 1 over 1 and 3 over 1. Well, that's just going to be 1 and 3. Now I'm going to take 1 and 3 and put them over 2. So one at a time, 1/2 and 3/2. 1/2 and 3/2. Now I've got to take 1 and 3 and put it over the 4. So 1/4 and 3/4. And yes, they're out of order, and that's okay. It's just the way we organized our work in generating the P over Q list. All right, so that's using the rational zero theorem to list the possible rational zeros. So what that means is that if this 5th degree polynomial function has any x-intercepts or zeros or solutions or roots that happen to pass through the x-axis at a rational number, it would have to be a number that's in this list. Likewise, in number 2, if this 3rd degree polynomial function passes through the x-axis in a rational number, it would have to be that rational number that passes, or that this graph passes through, is one of the numbers that are in our P over Q list. All right, so what are we doing with this list once we generate it? Well, let's look at example 3. Actually, I think it must be 4. All right, now find zeros of a polynomial function using the rational zero theorem. So when I read rational zero theorem, I want my brain to kind of real quickly connect, oh, that's that P over Q list. Okay, and then after I generate it, I've got to do some synthetic division looking for a remainder of 0. And then we continue from there. All right, so finding zeros using the rational zero theorem requires that first we list the possible rational zeros. Well, real quickly, I can see that P is 20. Constant is negative 20, but the absolute value is 20. And Q, notice, is 1. Well, if I generated a P over Q list, okay, and the only factors of Q are positive, negative, 1, then this list is actually just going to be the P list, the factors of 20. 1, 2, 4, 5, and 20. So taking all of these numbers and putting them over 1 would just result in the factors of P only. And I think I need a 10 here. 10 and 20. Double check. 1 and 20, 2 and 10. Yeah, 4 and 5. All right, so how do we find the zeros? So remember, that means that f of x would have to be 0. Well, to find zeros in the past, if we had a quadratic equation, we might factor or use the quadratic formula. If we had a cubic equation, but with 4 terms, we might have done factoring by grouping, factored and then set each factor equal to 0. Factor by grouping doesn't always work, and it doesn't work in this problem, so that's why we have to find another method for finding zeros. All right, so if this polynomial crosses through the x-axis, or even touches the x-axis, I should say, crosses or touches, has an x-intercept, then, and it's a rational number, it has to come from this list. All right, well, how do we know if any of these values would be a 0? Well, what we can do is we can do synthetic division to see if we get a remainder of 0, which suggests that we have a factor of this polynomial. All right. Oh, this is my line here to put the answers. All right, so we've done step 1, list possible rational zeros, P over Q. We've got our P over Q list. Begin testing with 1 and -1 and continue. So 1 and -1, 2 and -2, 4 and -5 until you find a 0 that is a remainder. So using synthetic division, let's say we're just going to predict that +1 is a 0. So up here I'll put the little 1. I'll put coefficients of all the terms, being careful to fill in any zeros if need be. Skip a line, bring the 1 down, multiply. This is 20. 20 times 1 is +20. Notice that we got lucky on the first try. It's not always the case that 1, when you try it first in synthetic division, will give you a 0. We just got lucky. Okay, what happens if you used 1 and you didn't get 0? Well, then you just kind of erase everything and you start all over and you test the next possible rational 0 of -1 up here to see if you get a remainder of 0. If -1 up here doesn't result in a 0, you move on to the +2. If +2 doesn't result in a remainder of 0, you move on to the -2, so forth and so on, until you find a rational 0. Okay, just a reminder, remember, these are coefficients of the 3rd degree polynomial. Okay, but when we did synthetic division, we divided, we got a quadratic factor. So I'm going to come down here and say, okay, x squared plus 9x plus 20 is a factor up here of this cubic. So if I set this equal to 0, now I know that with a quadratic, I can either use quadratic formula or I could try factoring to find the other 2 zeros. So when I have a cubic polynomial function, at most I'll have is 3 zeros. I found one of them. I found 1 0 to be +1. Okay, I could continue through this list trying all these other numbers up here, and I might get another remainder of 0. And I probably will. So if you wanted to find all the zeros by doing a bunch of synthetic divisions, that's fine, but it's tedious. If you have a cubic and you get down to a quadratic after finding a remainder of 0, let's just use our background. Let's factor this. And if not, use quadratic formula. So factor sum chart. It's kind of quickly doing the factoring here, but if you did a factor sum chart, you're looking for factors of 20 that sum to b or 9. That would be x, and it should be +4 and +5. I'm going to set each factor equal to 0. So from x plus 4, we'll get a solution of x equals -4. And from x plus 5 being set equal to 0, when you subtract a 5 to both sides, you get x equals -5. Okay, so I actually went ahead and found all the zeros pretty quickly. My zeros are x equals -5, x equals -4, and don't forget, this is a 0 too, because it gave us a remainder of 0 here, and x equals 1. At most, we would have 3 zeros of any kind on this cubic function. So let me go back and read the directions. Did I list the possible rational zeros? Yes, I did, P over Q. I began testing synthetic division with 1, and I got lucky. I got a remainder of 0. I ended up with quadratic coefficients, so I just let my previous knowledge allow me to factor and find the other zeros. I'm going to switch these two. We solved and we found all the zeros by solving this quadratic. So now that I switched them, we're asked to complete the linear factorization. And what that means is, I think I'll put it above number 3. That means that the original function right here could be factored into linear factors. So I'm going to leave a little space here. You should too. I have 3 zeros. If x equals -5 is a 0, remember it came from the linear factor x plus 5. Linear because the highest exponent is 1. X equals -4 came from the factor of x plus 4. And x equals 1 right here would come from a factor of x minus 1. So I could factor this cubic into these 3 linear factors. Now, I could also have any kind of constant number here that's being multiplied. Like I could have a 5 in front or a -10 in front. It wouldn't matter. I would still get these same 3 zeros irregardless of this constant right here. So usually we just kind of use this notation. We use a and then a little subscript n to represent any constant that might possibly be multiplied up front here that won't have any effect on these zeros. Okay, so P over Q list, starting with +1, or anywhere you want to, just as kind of a good entry point. Synthetic division, cubic to quadratic. Oh, quadratic, let me try factoring or quadratic formula. Listing all the zeros and then working backwards from the zeros to the factors that those zeros came from to complete what we call a linear factorization. All right, let's continue looking at another example. I think this must be 5. Take them off. Okay, let's look at the question. It says, find all the rational zeros using the rational zero theorem. Okay, find all the rational zeros. A little bit different language. All right, when I read rational zero theorem, I'm thinking P over Q. So it shouldn't be too bad for this because these numbers aren't too large. So P and then Q is 1. So the factors of P are positive, negative, 1, and 2. That's a pretty quick thing to generate. And Q would just be positive, factors of Q would just be positive, negative, 1. So it's really not really relevant to put that down. So nice, we only have 4 numbers to test to find all the rational zeros. Okay, so I'm going to just start with +1. Coefficients of this cubic. I don't need to fill any 0 placeholders. Notice I don't get a remainder of 0. I should have written this more lightly because now I'm going to have to go and erase. But you know what, I think I have a little bit of space here, so I'm just going to mark that off and I'm going to go to -1. Oh, that's going to be not a remainder of 0 either. So that tells me that -1 is not a 0. The graph doesn't cross or touch at x equals 1 nor x equals -1. So we only have 2 more possible zeros to try, positive and -2. Well, might as well try 2. It's possible that none of them are, that this equation doesn't have any rational zeros at all. I mean, this graph might not even be crossing through the x-axis. It does, but, you know, but it's possible in some problems. Oh, finally. So now I know that 2 is a 0. I mean, I might as well just go ahead and try -2. See if that's also a rational zero. I'm this far in. Actually, no. The only rational zero is +2. So So did we find all the rational zeros? Yes, we did, because we actually used all our possible rational zeros in 4 different synthetic divisions, and the only one that gave us a remainder of 0 was 2. However, there's more to this problem. They want us to complete a linear factorization. They actually want us to take this a little further and solve, meaning what? Well, let me come down here. Solve for the zeros. We already know that x equals 2 is a 0. There are actually going to be 3 zeros, but the only one that's rational is 2. The other 2 zeros, because there's always going to be 3 zeros. They might be rational, irrational, or some of them are even imaginary zeros. So how do we find the other 2? Well, we come back up here and we go, wait a minute. These were the coefficients of a cubic right here. And so these are the coefficients of a quadratic. So let me come down here and solve the quadratic where I had a remainder of 0. So 1x squared plus 3x plus 1 equals 0. I cannot factor this. There are not factors of 1 that add to 3, but it is quadratic, so I can use the quadratic formula. So I'll probably want to come over here and make sure I remember that A is 1, B is 3, and C is 1. Quadratic formula is opposite B plus or minus square root of B squared minus 4 times A times C, all over 2 times A. So keep the -3, don't forget the plus minus, and you got the 2 down here. Now we'll focus our attention right here. So this is 9 minus 4, which is 5. So actually we have irrational zeros. So we had one rational zero of 2, and when we use quadratic formula, we get 2 irrational zeros. And we're going to always have pairs of irrational zeros, because what happens is you're always going to have the plus irrational and the minus irrational. So if I wrote this out separately, it'd be -3 minus square root of 5 divided by 2. And the other 0 is -3 plus square root of 5 divided by 2. So I did find all the rational zeros. I found 2, but and along the way, I found 2 irrational zeros. So when it says solve for the zeros, it means all of them here. Okay, now to complete the linear factorization, I like to do that last. So now that just means, okay, well, back up here at this function, I have 3 zeros. So I'm going to have 3 parentheses because I have 3 factors that these zeros came from. And then I always might just have this random constant. It doesn't have to be 1. It can be any number. So that's kind of the format here. Okay, so for this 0, it came from the factor x minus 2, not x plus 2. And here's where it gets a little tricky. So right here, I'm going to do x minus. So for this one, x minus and x minus. Okay, I always take the opposite. Notice we're taking the opposite. So in the numerator, I'm going to take the opposite of all the signs. So this is minus minus. So I'm going to change this to plus plus. So x plus fraction 3 plus square root of 5 over 2. So for this factor that's going to contain this 0 where this 0 came from, I'm going to do plus minus. So plus, and then 3 minus square root of 5 over 2. It's a little bit weird when you're dealing with these kinds of zeros. All right. Okay, let's do one more. Let's do example 6. All right, it says solving polynomial equations, find all zeros, even if they're irrational or imaginary or rational. So it says you must continue to divide synthetically until you have a quadratic. So we'll see what that means in a minute. Notice that this function is a 4th degree function. So it's set equal to 0 already. Let's list the factors of P and Q. And actually I can see again that Q's factors are just positive -1. So P over Q factors are just going to be the factors of 13, which are just 1 and 13. So we only have 4 to test, I guess. All right, so if this fourth degree function passes through an irrational zero, it'll come from one of these 4 numbers. So I'm just going to start with 1 and hope that we get kind of lucky here. So 1. And there's no missing terms from fourth all the way down to the constant. Yeah, so I don't have to fill in any zeros. Wonderful. All right, so I'm going to come down here. X equals 1 is a 0. And I should have 4 zeros. So I'm just going to kind of get my list ready right here. So x equals 1 is a 0 because I have a remainder of 0. So remember, these are coefficients of a fourth degree function. These are actually coefficients of a third degree function. I can't use the quadratic formula on a third degree function. I can only use the quadratic formula on a second degree function. So what that was saying here is you must continue to divide synthetically until you have a quadratic. Well, I don't want to go back to n equals 4. I want to stay with n equals 3. So what we do is we come up here and go, okay, I've got to continue to divide synthetically, but now let's use these new coefficients. Right, which means now I can actually try positive 1 again. It's not off limits. X equals 1 might occur twice. So that's what I would do. I would go ahead and start all over and use the same one I used here, but with these new coefficients. Remember, these are the coefficients of a cubic. So if I divide and get a remainder of 0, I will have coefficients of the quadratic and then be able to use the quadratic formula. I guess test again could have been down here, but I just wanted to use this space. I'm going to try 1 again. And I got lucky. Had 1 not worked, I would have gone to -1, then 13, then -13. So this is great. So now I know that x equals 1 occurs twice. It's what we call a double root, multiplicity of 2. So the graph probably touches, doesn't cross the x-axis at x equals 1. Right now I'm going to solve the resulting quadratic. So x squared minus 4x plus 13 equals 0. It won't factor, so I've got to use quadratic formula again. So opposite b, that's already negative, so we'll make it positive. B squared minus 4 times a times 13, all over 2 times a. I'm just going to bring down the 4 and the 2. And don't forget the plus minus. 16 minus 52, well, that's going to be a -36. This is imaginary because we have the negative under the radical. So if I take out the negative, change it to an I, and then square root of 36 is where my attention lands. Square root of 36 is 6. So I'll keep the 2, I'll keep the 4. This becomes 6i. And now that I see that the numbers 4, 6, and 2 all have a common factor of 2, I will divide a 2 out from 2, leaving 1, and a 2 out from 4, leaving 2, and a 2 out from 6, leaving 3. Unless all 3 of these numbers have a common factor, you can't simplify. So my answers are 2 plus or minus 3i. So when we record those over here, we're going to have 2 minus 3i and 2 plus 3i. I knew I should have 4 zeros because the highest exponent, the degree, tells you how many solutions you should have, how many zeros. So notice that of my 4 solutions, I can say 2 of them are rational and 2 of them are imaginary. Okay, and to complete the linear factorization, if I call that function f of x, I can have that constant here. And because I have 4 zeros, I've got to have 4 factors. So x minus 1 twice. And then always start with x to be a factor. And then take the opposite of both these signs, because you're really just like moving both these terms over to the x side. So minus 2 plus 3i. And you're moving both these terms over to the x side, so they'd both be minus 2 and minus 3i. Okay, we'll continue with the rest of the content in the next lesson.